Yeah. Let's start with first discussing some basics of group 15. First, you must know these important names which are directly asked in JEE mains as well. One is chili salt, Indian salt peter. This is called chili salt peter. Indian salt peter and floor appetite. Calcium 9, phosphate 6, and calcium fluoride. Floor appetite. Okay.
Yeah.
And now notice as it comes to nitrogen always shows an anomalous behavior. It is because it can have a very strong p-pi bond. Got it? The type of bonding what it goes is between 2p and 2p. While if you talk about the single bond strength, however, pp will have a stronger bond compared to nn. And this is because it would have a high interatomic repulsions. Got it? While pp bond on the other hand will have single bond with less amount of interatomic repulsions. Here the interatomic repulsions are much stronger. And unlike phosphorus, arsenic, antimony and other group elements, nitrogen cannot make a p-pi-d-pi bond, which means it cannot expand its octet. So the maximum covalency, that means the maximum number of bonds, right? So let me just highlight that here. Maximum covalency, maximum covalency of nitrogen being only 4. 4 bonds only it can form to the maximum. While phosphorus arsenic can have a stronger d-pi bond also. Okay.
Yes, sir.
They can easily associate with alkyl group as a part of ligands. Next,
Yes.
if you notice down the physical properties, nitrogen, phosphorus are generally non-metals, antimony, arsenic are metalloid, and bismuth is a metal. Down the group, if you go, ionization energy decreases, atomic size naturally increases, metallic character also increases. If you compare melting point, nitrogen is less than phosphorus, less than arsenic, while arsenic is greater than antimony, greater than bismuth. This is about the melting point. While boiling point goes very similar, okay. And as it comes to antimony, this is what would happen. Got it? Bismuth, in fact, would come somewhere just before the antimony. Got it? So bismuth अगर आपको देखना है, so this is what it should be. Got it? So I can just put that here. Arsenic less than bismuth less than antimony. Another thing we need to remember is the electron affinity. Okay? Or delta H of electron gain enthalpy. Electron gain enthalpy in this case for nitrogen it is positive and for all others are negative. And you notice delta H of electron gain enthalpy, correct? If I take the mod value, it will be decreasing down the increasing down the group. Unlike in other cases where it will decrease, यहाँ पर ये increase होगा. Okay.
Yes.
So this is one exception when it comes to group 15. All the elements of these groups are polyatomic. Dinitrogen is the only one which is the diatomic form. Rest all are solids. Metallic character increases down the group, correct? And you see Generally, the boiling point increases from top to bottom, but melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all shows allotropy. Okay, these are important statements from NCRT. In case of reactivity, for hydrides, if you notice, from top to bottom, stability decreases, bond dissociation energy decreases.
Hmm.
Okay,
Yes, sir.
you can see when it comes to oxidizing ability will be similar to that of stability. Reducing ability is inversely proportional. Oxidation state is inversely proportional. Acidity is inversely proportional. Okay, which means, let me just put you in terms of the term here. For example, if I take NH3, PH3, ASH3, SbH3, and um, BiH3 here, if we say this is top towards bottom, reducing ability increases. Okay, stability stability of the compounds decreases. Oxidation state, I mean, if it comes to acidity, acidity of the hydrides decreases down the from top to bottom. Got it? Basicity also decreases. Got it? The reason being here the acidity is with respect to H plus. Correct? So the H plus formation itself is not observed. Moreover, down the group basicity, sorry, I sorry about the acidity part will increase because electron negativity wise between these three you can still compare. Acidity increases, basicity decreases. This is typically how it goes for hydrides. Next, you can see stability decreases. Okay, bond strength decreases down the group, that is bond dissociation energy or bond strength, both will decrease here. Next, acidic strength increases down the group, reducing nature increases down the group. Ammonia is mild reducing agent, but BiH3 is strong reducing agent. Melting point, you can see ammonia will have greater than pH3 because of hydrogen bonding. There are two types of oxides they can form, E2O3 and E2O5.
Hmm.
You can see oxidation, as it comes to oxidation state, if oxidation state increases, acidic character always increases. And top to bottom, you will see acidic strength decreases. That means oxidation state is also less stable. Higher oxidation states are less stable, while basicity increases. And that's why N2O3, P2O3, P2O5, these are all acidic, while Bi2O3 is basic, AS2O3, Sb2O3 is amphoteric in nature. Okay.
Hmm.
The type of halides they form is EX3, EX5. Higher the oxidation state, more is the covalent character. And if you recall, polarizing power psi is directly proportional to the charge of cation, charge of anion, and inversely proportional to size of the cation, directly proportional to size of the anion. Okay.
Hmm.
So since the plus phi has high polarizing power, it will show more covalent character. Next, with metals, they exist in a -3 oxidation state. So nitrogen you can see has -3, phosphorus has -3, arsenic has -3 in this case. Okay, next. As much as group 16 is concerned, correct? What are the terms we should know? They are generally called chalcogens. The
Hmm.
important compounds of oxygen include gypsum, Epsom salt, and barter. Barter. That is calcium sulfate dot 2H2, magnesium sulfate dot 7H2, and BaSO4. These are the terms we should know. Sulfur compounds which you should be aware is galena, zinc blende, and copper pyrites. Copper pyrites usually भूल जाते हैं बच्चे, so please do check what exactly is the structure of formula of copper pyrite. Next, ionization energy typically decreases down the group. Let me write down that part as well. So if you compare top to bottom, ionization energy decreases. Okay, electronegative character decreases. Okay, atomic size of the atom increases. Got it? Next, metallic nature increases down the group. These are general fundamentals or general parameters. Exceptional parameter is electron gain enthalpy. What you would notice is sulfur is greater than selenium, tellurium, polonium, and last comes oxygen. So oxygen has the least electron gain enthalpy. Okay. Next, if you compare the ionization energy of the first element, like nitrogen will be greater than that of oxygen. But if it comes to second one, oxygen will be greater than nitrogen. Okay. Even as it comes to the third one, if you compare nitrogen and oxygen will be greater than nitrogen. Second thing, you should also know that ionization energy of N2 molecule is greater than ionization energy of N atom, while ionization energy of O2 molecule is less than ionization energy of oxygen atom. The same logic goes to even fluorine. So ionization energy of F2 is less than ionization energy of F. Okay. So keep this in mind as it comes to ionization energy, how to compare them. Is that clear, beta? Next, if you compare the physical properties, oxygen and sulfur are non-metals. Oxygen typically exists as a diatomic form. Sulfur exists as both S6 and S8, but S8 existence is much more familiar than S6. Okay, and that is much more familiar than S2 also. So there will be small quantity of S2 will also be observed. Selenium, tellurium are metalloids.
Yes.
Polonium is a radioactive metal. Notice chemical properties. Stability of oxidation state increases. Lower oxidation state increases here due to inert pair effect. Okay, which means down the group the +6 oxidation state decreases. +4 oxidation state increases. Oxygen, on the other hand, shows a lot of variability in oxidation state that includes -2 to +1. Okay, these are all the compounds which will show various oxidation states. Water is
Hmm.
generally in liquid state due to high hydrogen bonding. H2S exists in gaseous state as much as hydrates are concerned.
Yeah.
Down the group, the bond dissociation energy decreases for hydrates. So stability decreases, bond strength decreases. Acidic nature increases, reducing power increases. Okay, and you will see
Hmm.
water is not a good reducing agent. Okay, but rest all can act as good reducing agent.
Hmm.
Next, if you compare acidic strength, H2T is stronger acid than H2S.
Hmm. Yes.
Forgot to write boiling point and melting point. Boiling point and melting point typically, overpowers here by hydrogen bonding, and then comes H2Te, H2Se, and H2S. Next,
Yeah.
the type of oxides they can make here are EO2 and EO3. Oxygen can make O3, sulfur can make SO2 and SO3. These two are generally gases. SeO2 is solid. Down top to bottom, if you see acidic strength decreases, reducing ability decreases. SO2 is a reducing agent. TeO2 is an oxidizing agent. Okay. Ozone structure usually have like this with 6 lone pair electrons here. Okay.
Hmm.
And as much as halides are concerned, fluorides you can see stability varies this way. Okay. And EF6 is the only species which is stable, which is gaseous and extremely inert, specifically with sulfur.
Hmm.
If you have any monohalides of either sulfur or selenium, they both disproportionate into +4 and 0 oxidation state. Got it?
Yes.
So, like this is that basic information you need to learn it from NCERT as much as physical properties or general properties are concerned. Next, group 17. CaF2 is called fluorapatite. Na3AlF6 is cryolite. And sorry, this is fluorspar. And fluorapatite is Ca3PO4 twice and CaF2. Or if you multiply this 3 times here, it will become Ca9 and PO4 6. That also I told you. In another way, you can write it that way. Carnallite, KCl MgCl dot 6H2. That is carnallite. Now see, usual properties will always, you know, decrease down the group or increase down
Hmm.
the group. While electron gain enthalpy is one such property where chlorine is greater than that of fluorine. In fluorine, you will see because of the smaller size of the fluorine, it will have repulsions between the atoms. And that's why it will not be able to release a lot of energy as that of chloride.
Yes. Sir.
Sorry, I wrote it wrong here. It should have been Cl, only Cl, not F2 and all. Okay, like this. Atom. Clear beta?
Yeah.
So fluoride will have strong uh, inter-electronic repulsions. Got it? I will put that word also. Strong Inter-electronic repulsions. If we compare as a molecule, Cl2 is having greater bond dissociation energy than bromine, than fluorine and iodine. Now here it is due to the electron pair repulsions. That is, if you take this pair and this pair, this will have stronger repulsions. Because of fluoride being smaller atom, the electron repulsion is much stronger. That helps in breaking the bond easily.
Hmm.
Down the group, in any case, bond length will always increase. All halogens are typically colored. They absorb light from the visible region. Hence, F2 is yellow, chlorine is green yellow, bromine in the liquid state is red, iodine in solid state is violet.
Hmm.
While these two are, these three are easily soluble in water, while I2 is insoluble or less soluble and more soluble in organic layers. F2 is the strongest oxidizing agent compared to all the compounds. Of course, it is stronger than Cl2. And if you compare the overall oxidizing agent ability, F2 is stronger than Cl2, then Br2, then I2. So reactions like this, like Cl2 plus 2I minus, can easily oxidize, I2, I minus to I2, and this will get reduced to 2Cl minus. Similarly, if I have Br2, if you have Cl2 plus 2Br minus also, you will get the same thing. You will get it as Br2 plus 2Cl minus. And similarly, if you have Br2 plus 2I minus, it will convert this into I2 plus 2Br minus. Okay.
Yeah.
Chemical properties wise, fluorine exhibits only one oxidation state, which is -1. And oxidizing oxidizing ability, if you compare down the group, it decreases. Okay, in aqueous medium. As it comes to standard electrode potential, these are the three fundamentals we always look into. What is the bond dissociation energy? What is the electron gain enthalpy? And what is its hydration energy? Okay. Now, basic reactions wise, if you notice, fluorine reacts with water to give O2 and HF. Chlorine water will give you HCl or HBr and HOCl, hypohalous acid. I2 is non-reactive. However, if you have I minus in water, correct, it can act like an oxidizing agent. It can get oxidized to I2. Got it? But there must be some reagent along with it. It's a good reducing agent. Reaction with F2 are exothermic, and HF has a very high boiling point in comparison to the other hydrates, which means if you compare HF boiling point, this will still be greater than that of HI, greater than that of HBr, greater than that of HCl. You can see the reactivity. X is giving HX, top to bottom, you can see stability decreases, bond dissociation energy decreases, acidic strength increases. And that's why HI is the strongest acid compared to HBr, HCl, and HF. This is the acidic strength. As much as the oxides are concerned, oxygen makes OF2 and O2F2. OF2 is thermally more stable than O2F2. These compounds are called fluorinating agent. That means they can provide fluorides more easily. Okay.
Yes.
So if you take a new radioactive elements like Pu and react with O2 F6 F2, you can easily get Pu F6, which is used in nuclear fusions. Okay, as a nuclear
Yeah.
fuel. And oxide stability, if you compare, iodine will make better oxide stability compared to chlorides compared to bromides. It is because iodide will have better polarizing power as compared to that of uh, chloride and bromide. Now, this is due to the vacant d orbital. Okay. Hmm. Next, chloride oxides, if you compare, they can have Cl2O, Cl2O2, Cl2O6, and Cl2O7. Okay. These are going to be, highly reactive oxidizing agents. They tend to explode. While bromine exists as Br2O, BrO2, and BrO3, they are less stable, but they are powerful oxidizing agents. While I2O4, you can check it out clearly that I2O4, I2O7, I2O5, these are okay or good oxidizing agents. They are insoluble solids. They can be decomposable, but they are still stable compared to the other oxides.
Hmm.
Right, beta? Next.
Yes.
Top to bottom, if you compare, the ionic character decreases, and you see metal fluorides will be greater than chloride, bromide, and iodide in terms of ionic character, and halides are more covalent in generally, correct, as you go towards the higher oxidation state. Which means if you compare tin with a chloride, these two will make a covalent bond compared to that of SnCl2, which is ionic. And reactivity wise, if you notice, fluorine is definitely more reactive. Then comes interhalogens. Interhalogens are relatively more reactive than chlorine, bromine, or iodine. Okay.
Yes.
Interhalogens will have sufficient polarity that also makes them to have high boiling point. Okay. Next, if you compare all the boiling points of hydrates and melting point of hydrates, so this is the sequence that you need to remember. As it comes to 15, 16, 17, you can see these are all the melting point order. This is all the boiling point order. Okay.
Hmm.
So as much as the melting point is concerned, you can see first ammonia, then SbH3, ASH3, and PH3. That will be the melting point order. Here water, then tellurium, selenium, and sulfur. Here
Hmm.
Hi, then HF, then HBr, then HCl. This is about the melting point.
Hmm.
Boiling point is concerned. Sorry, here when I wrote boiling point only. Okay. As much as boiling point is concerned, you can see SbH3 will be greater than NH3, then ASH3 and PH3. While in water, if you compare water, both boiling point and melting point will be high. So these two order will be same in the case of group 16. Okay. While here
Yeah.
boiling point will be HF greater than that of HI, HBr, and HCl. This will be the order of boiling point. Okay. All
Yes.
of these ammonia, water, and HF is high due to hydrogen bonding. Okay. Now, if
Yeah.
you compare the boiling point of these three, sorry, melting point of these three, water, ammonia will have almost closer melting points than HF. While when it comes to boiling point, definitely water is greater than ammonia is great. Sorry, water is greater than HF is greater than ammonia. This is the boiling point order. Okay.
Yes.
Let's check group 18. They're generally called noble gases or inert gases because they have fully filled valence orbital electrons. And they called inert gas because they are chemically unreactive. Ionization,
Hmm.
in comparison to their respective periods, they will have the highest value. Electron gain enthalpy, all of them have positive value. Within that, if you compare here, you can see how is the correct order. Neon is greater than argon. Argon and krypton are almost the same. Then comes xenon, and then comes helium. Okay, this is the order of electron gain enthalpy. Very important order. So please do remember that. Okay,
Hmm.
which means neon will give require high most positive value. This is all about positive values.
Yeah.
However, when it comes to melting point and boiling point, it simply increases down the group, which means if you have to compare helium, that will be the lowest boiling point ever, 4.2 Kelvin. Physical properties wise, if you notice, these noble gases are monoatomic, colorless, odorless, tasteless, very low melting point because they have a very weak dispersion force of attraction or van der Waal attractions.
Hmm.
They liquefy at a very low temperature. Noble gases are least reactive, correct? They have very high ionization and positive electron gain enthalpy. Xenon is the only compound which can show the molecular forms as XeF246O3, OF4, O2F, F2, and so on. You see, XeO3 is colorless explosive solid and have a pyramidal molecular structure because it is in the form of AB3L1. Okay, one lone pair
Yeah.
and three bonded pairs. While XeoF4 is colorless volatile liquid having square pyramidal molecular structure. It allows square pyramidal molecular structure.
Hmm.
Next, if we compare the uses wise, lithium is a light gas. It is cryogenic agent. Okay, used in NMR spectrography and MRI machines.
Hmm.
Used as a divalent, divalent for oxygen in diving apparatus. That means it will be mixed with the oxygen to make the cylinders lighter, okay, and sustain high pressure.
Hmm.
And most importantly, as it get into the bloodstream, because of its low solubility, as the divers come to the surface, the helium gas easily comes out of the body.
Hmm.
Neon is used in discharge tubes, fluorescent lamps, and greenhouses. Argon mainly used in metallurgical process for alloys and metal makings. It is inert at high temperature. Okay. Now notice, as much as the reactions are concerned, these are the few reactions we might need to learn. Although chances of asking are less, but it might be asked in a different pattern. Okay, it might be asked as
Yeah.
uh, not as a chemical reaction, like what is the importance of the product and so on, or what is the name related to that product. For instance, like this Haber process, it is for ammonia synthesis. So you can see nitrogen, ammonia reacted in the presence of iron at such high pressure and temperature, you will get ammonia. Next one is Oswald's process. This is for nitric acid preparation, where we use platinum or rhodium gauge catalyst, where 4 moles of ammonia and 5 moles of O2 reacts to get NO and H2O.
Hmm.
This we usually use it in reference of redox reactions, so keep that in mind. A balanced equation can be asked. Okay.
Hmm.
Basically, once you generate NO in aerial oxidation will undergo NO2 formation, and it is that NO2 when you react with water becomes nitric acid. Next is sulfuric acid, that is done by contact process. We make sulfur dioxide by heating the sulfur form in excess of oxygen. And as you get this SO2, we further react with O2, but this time in the presence of vanadium pentoxide, okay, at high temperature and pressure, that will convert into SO3. The SO3 gas will get, added to H2SO4. I mean, of course, first it will get hydrolyzed, forms H2SO4. So we cannot store sulfuric acid in a pure form. So we add excess amount of SO3 so that it can convert into a form known as oleum, H2S2O7.
Hmm.
H2S2O7 plus water will give you H2SO4. So that's how typically we can prepare the sulfuric acid. Next, decon process is for preparation of chlorine gas. That is, we take 4 moles of HCl with O2 in the presence of CuCl2 to get 2 moles of Cl2 and 2 moles of water. This
Hmm.
is called decons process. So as much as NCRT, 15 to 18 groups are concerned, this is something you
Yeah.
should know. Hmm?
Okay.
Next, check out the acidic type of acids and their names. Okay, usually the highest oxidation state, if only it is +7, it is termed as per-ic acid, perchloric acid, permanganic acid. Okay, like that. And oxidizing state as it decreases, you will first remove the per, you'll only put ic, and further decreasing oxidation state, you'll make it as us. If the least amount of oxidation state is there, you call it as hypo. Usually hypo is used when you have +1 oxidation state. Okay.
Hmm.
Meta is if you take an acid, remove one water molecule. Pyro is take two acid molecules, remove one water molecule, then it will become pyro. Ortho acid means same acid. That means original acid, whatever it is there, it is called ortho acid.
Yeah.
So you can use. If this is phosphoric acid, then meta means remove one water molecule out of it, so it will become HPO3. If it is pyrophosphoric acid, make two molecules, then remove one water molecule, it will become H4P2O7, that is pyrophosphoric acid. Ortho means original form. This is original
Hmm.
form. Phosphorus acid also, it will become metaphosphorus acid, HPO2. Pyrophosphorus acid, removing water from 2 moles. Orthophosphorus acid or phosphonic acid. The alternative name is called phosphonic acid. Correct?
Hmm. Yeah.
Next, hypophosphorus acid is H3PO2. Okay. And now notice, if you get pyrophosphoric acid, right? This is pyrophosphoric acid. Just remove one oxygen out of it. You will get H4P2O6. And that is hypophosphoric acid.
Yeah.
Next one. Phosphenic acid. H3PO2 is called phosphenic acid. Oxidation state is +1. It has one POH bond, two PH bonds, and one P double bond O bond. So this is the structure of it. Orthophosphorus acid, which is phosphonic acid with oxidation state +3. The basicity is 2, one pH bond and one P double bond. Pyrophosphorus acid is basically you add 2 times, remove water, and you'll get this one. So you'll have 4 POH bond, one POP bond. Hypophosphoric acid, okay, that is H4P2O6. Here phosphorus have one linkage. So far you will not
Yeah.
find any phosphorus linkage acids except this one.
Hmm.
Orthophosphoric acid is simply H3PO4. Pyro is double this, remove water out of it. Okay.
Yeah.
The basicity for that is 4. Correct. You can notice these structures quickly. Okay. The hybridization in all of them is sp3. All of these are sp3 hybridized orbitals. Okay, beta.
Yes.
As much as sulfur is concerned, we need to check one sulfur structure as well as its acidic structures. So notice H2SO4 is sulfuric acid. If you add 2 moles, remove 1 water, you will get oleum, which is uh, pyrosulfuric acid. Now imagine adding one oxygen. If you add one extra oxygen, it will come between two sulfurs like this. SOOS bond like this. Okay. If you get a bond like this, then we use the terminology peroxy. So that's why it is called peroxodisulfuric acid. It's called peroxodisulfuric acid. Sulfurous acid, you know that it is H2SO3, and this can also have a pyrosulfurous acid. Okay.
Hmm.
Next, S8, if you notice, S8 can be existing as a crown shape. This is a crown shape structure with a bond angle of around 107 degrees. The hybridization on every sulfur is sp3 hybridization. While it can also exhibit in S6 form where the bond length is longer and bond angle is shorter. Okay, as compared to that of S8. So it's a clear evidence that as compared to S8 and S6, which is more easily breakable, this one, because the bond length here is longer. Okay, next.
Hmm.
As it comes to sulfurous acid, it is H2SO3, and if it comes to sulfuric acid, it is H2SO4. Then we have peroxodisulfuric acid, H2S2O8, right? It has a
Yeah.
common name also, okay, known as Marshall's acid. Marshall's acid. Similarly, I can have pyrosulfuric acid, which we call it as oleum. One more acid which you have is S double bond O, and one OH here and one OOH here. Okay, got it. So what do we have here is, you know, peroxo, peroxo monosulfuric acid or simply sulfuric acid. So instead of
Hmm.
having simply H2SO4, you have one extra oxygen, which is S2SO5, and this is called as Carros acid.
Yeah.
Okay, beta. These are the types of acids that you need to know it from sulfuric acid. There are two more acids that you would better remember when it comes to sulfuric acid. One is S double bond S, double bond O, OH, and OH. So instead of basically this oxygen, we are replacing one sulfur. That's it. Okay.
Yeah.
So this is called thiosulfuric acid. So whenever oxygen is being replaced by sulfur, you use the word thiosulfuric acid. So formula is H2S2O3. Okay.
Hmm.
Now, if you make any connections between the sulfurs here like this, direct connections here like this, OH and OH. Okay. So it is called thionous acid, or it depends upon how many number of sulfurs you are putting it at the center. So by chance,
Yeah.
if at all I put two more sulfurs here, so it will become four sulfurs. So that's why this is much more used or more frequently used. Okay. Uh, this is called tetrathionic acid. Tetrathionic
Yeah. I got it.
acid. There are four sulfurs, that's why it is tetra. Here there are two different oxidation states. These two sulfurs possess zero, while these two sulfurs possess plus 6 oxidation state.
Hmm.
Okay, beta. Right.
Yeah.
As much as chlorine is concerned, you will have hypophosphorus acid, which is HOCl, where chlorine has plus 1 oxidation state. Then we have chloric acid, then we have chlorous acid, which is HClO3 with plus 3 oxidation state. Then we have chloric acid with +5 oxidation state. And lastly, perchloric acid with +7 oxidation state. These are the respective structures for it. Okay.
Hmm.
All good, beta?
Yes.
Right. As much as group 13 and 14 is concerned, now you see, when it comes to general configuration of p block elements, we will usually write it like this: ns2 np 1 to 6. So by chance, if it is np1, then that is group 13, and if it is np6, then that is group 18. Correct.
Yeah.
So you can notice that there are 6 group of p elements in the periodic table, numbering from 13 to 18: boron, carbon, nitrogen, fluorine, helium, the groups. Okay.
Yes.
Next. Now see, difference in inner core elements greatly influence their physical properties such as atomic size and everything, as well as the chemical properties. Okay.
Hmm.
The maximum oxidation state, ये वाला important line है. So you can see the maximum oxidation state shown by the p block elements is equal to the total number of valence shell electrons. That is sum of s and p electrons. That is a maximum oxidation state. Okay.
Yes.
Now this line is also important. In addition to this, so many group oxidation state p block elements may show other than oxidation state, which normally but not necessarily different from total number of valence electrons by 2 units. Okay. So
Hmm.
usually मतलब ये हमेशा important condition नहीं है, but that could be the usual form, that it will be a difference of those 2 units. For example, if you have group 15, मतलब group 5 है, ग्रुप 5 में से 2 इलेक्ट्रॉन्स निकाल दो तो कितने हो गए 3. सो दैट कुड बी द ग्रुप ऑक्सीडेशन स्टेट. क्लियर.
Hmm.
नेक्स्ट, boron, carbon and nitrogen families, right? The group oxidation state is the most stable state for the lighter elements in the group. Okay. So group
Yeah. Yeah.
oxidation state is the uh, most stable for lighter elements in the group. Lighter elements as in boron, carbon and nitrogen itself. Okay.
Yes.
So if you notice the boron here, boron would be 3, carbon would be 4, nitrogen would be 5.
Yes.
Got it? And the occurrence of the oxidation states of 2 unit less than the group unit, the occurrence of oxidation state less than the 2 units, that is typically attributed to inert pair effect. Inert pair effect as in it is result of lanthanoid contraction observed in the last elements, that is thallium, lead, and bismuth. I mean bismuth onwards. Okay. That's why if you notice the oxidation states here, the group oxidation state +3, which is more stable and decreases down the group, and less than 2, less than 3, how much we have 2. So if it comes to 2, this is the oxidation state, which is a kind of a group oxidation state, but thallium down the group that will increase. Same logic with group 14 here and with +4 and +2, group 15 plus with +5 and +3. Okay. After group 15, the ability to showcase group oxidation state here like this. Okay. That slightly changes. That means if it comes to group 16, now I cannot say that oxygen will have +6 oxidation state, which is more stable. No. Okay. Now this time it is sulfur, which can show +6, selenium can show +6, and tellurium can show +6, but the higher stability is like this. While +4 oxidation state will decrease towards selenium and towards tellurium. Is this point
Yes.
clear, beta?
Yeah.
Next. So just remember this terminology. Group oxidation state is +6, +7, and +8 for 16, 17, and 18. But the other oxidation states which can occur are these. Okay. Next, the non-metals and metalloids exist only in p block of the periodic table. The non-metal character of elements decreases down the group. Okay.
Hmm.
Non-metals have high ionization enthalpies and high electronegativities than the metals. Got it? The group formed by highly reactive non-metals which react with reactive metals are generally ionic because of their large electronegative differences. We are talking about like uh, group 1, group 2 versus these non-metals. Okay.
Hmm.
Next, you see the non-metal oxides are acidic or neutral, whereas the metal oxides are usually basic in nature. Okay.
Yeah.
So this is the list of basic oxides, acetic oxides, and amphoteric oxides that we must remember. Got it?
Hmm.
So group 1, group 2, except BeO and Tl2O, rest all are okay, except BeO. I mean, Tl2 is a basic part only. This is basic only. So these are all basic oxides. While acidic oxides are these, amphoteric oxides are these. Okay.
Hmm.
Next, if you notice, first is the size and the other properties which depends upon the size here. And see, the second important difference which applies only to p block elements arise from the d orbital valence shell heavier elements which will be involved and their lack in the second period elements. Okay. So I told you that the maximum covalency is 4 for boron, carbon, nitrogen, oxygen, and fluorine. Okay. See, boron forms only Bf4 minus while aluminum forms Al F6 minus. Okay. Important statement question. So do remember this line. Okay. It could be directly asked. The reason, what is the reason, beta? The presence of the d orbital influences the chemistry of heavier elements like aluminum in number of other ways as well. Okay. So that gives the availability of dd orbitals. Okay. And you see, first member of the group differs from heavier elements, heavier members, due to its p-pi bond formation, like in the case of carbon, in the case of nitrogen, and in the case of oxygen. So all these combined cases. And next, as the d orbitals are higher energy than p orbitals, they contribute less to the overall stability of molecules than does p-pi bonds. However, the coordination number in the species of heavier elements may be higher than for the first element in the same oxidation state. For example, plus 5 oxidation state, both nitrogen and phosphorus forms oxoanions. NO3 minus, okay, which is oxoanion, with pi bond involved in one nitrogen orbital, and PO4 3 minus, which has four coordinates involved, sp and d, contributing to pi bond. So basically here emphasis is mostly about group 13 and 14. You can see
Hmm.
boron is typically non-metal. This line is important for us. Aluminium is metal but shows many chemical properties like similarities to boron. And gallium, indium, and neohium are almost exclusively metallic in character. Okay, next. The type of boron is observed mainly in orthoboric acid, borax, as well as kernite. Okay,
Yeah.
boron exists in two isotopic forms, beta. One is boron 10, the other one is boron 11. Boron 11 is more observed. Correct.
Hmm.
And aluminum is the most abundant metal, while the third most abundant element on the Earth's crust, after oxygen and silicon.
Yeah.
You can see L2O3.2H2 and cryolite are important minerals of aluminum. Okay. Now, this is important line again. Neohium has the symbol NH and atomic number as 113. The configuration for that is important. Basically, down the group, you can see the configuration is about 7p2. Okay. And you see the half-life of neohelium is how much? 20 seconds. That's it. These pointers are important for us. Next. The outer configuration is Ns to Np1, and gallium indium has noble gases, thallium has noble gases plus 14 F electrons. And as it comes to atomic size, this is an exception which is only observed in group 13, where gallium is slightly lesser than aluminum. So this is how the size varies. Okay, and see the presence of additional 10 electrons offer poor shielding. Okay, and ionization enthalpy wise, if you observe, correct, the order of,
Hmm.
you can see that the observed discontinuity here, boron will be the highest, correct, and then the observed discontinuity in the ionization energy values between boron and gallium, okay, and between indium and thallium is due to inavailability of d and f electrons. In generally, the ionization 3 is greater than that of 2 and 1. Okay. Next, electron negativity first decreases and then increases marginally. And you see that physical properties wise, if you compare, its high boiling point makes it useful material for measuring high temperatures. Okay. We are talking about the gallium here. So gallium unusually has very low melting point and could have high boiling point. So its high boiling point, I mean the difference in melting and boiling point is so high that it can be used, for measuring high temperatures. Okay, this is the form we need
Yeah.
to remember. And as much as the oxidation state is concerned here, you could notice that both can show +1 and +3 oxidation state, and the stability of +1 progressively increases for higher elements here. That means thallium shows more stability in +1. I want you to emphasize more on the ionic size first. So you can see ionic radius is gradually increasing. There is no problem in terms of boron +3, Al +3, gallium +3. While if you compare to the ionization enthalpy, first ionization, because you should be focused more on that one. So you can see the boron is the highest, and then directly comes thallium. That is important. That is thallium. And afterward comes gallium, aluminum. These two are almost the same, and the least comes indium. So that's one important ionization which I have written it here. You can see. And next, electronegativity is a gradual change except for aluminum. Aluminum will be the last one. Okay, so this is the electronegativity part. You can see that same logic here also.
Hmm.
Melting point and boiling point, you can see boron has exceptionally high melting point. Between these three, there is a change. Boiling point, if it comes to first two, is okay. I mean, first three are okay. Then indium and thallium. That is the value for boiling point.
Hmm.
So, if you ask me, this is the takeaway, important takeaway from group 13. Hmm?
Yeah.
Next. The tendency to behave like a Lewis acid would be more observed and increases with increase in the size down the group. Okay, so which means you can see here tendency to behave as Lewis acid, sorry, decreases as you increase the size. So if you compare BCl3 versus AlCl3, so BCl3 is a stronger acid. Okay,
Hmm.
and AlCl3 on the other hand can attain stability by forming this dimer formation here. Okay, so you can see that the bond length, there are two different bond lengths, 206 and 221. The bond angle outward is 118, inside is 101 and 79. These are the different bond angles of the tetrahedral geometry what it has. Okay, the type of bonding, this is having a banana bond here. So you know that this is one banana bond like this. And the banana bond, what we call it here is three centered, four electron bond here. While
Hmm.
this particular covalent bond, this is a covalent bond which you call it as two centered, two electron bond. So basically you have one, two, three, four. Four two centered two electron bond and two three centered four electron bond. Okay.
Hmm.
Next. The trichlorides on hydrolysis in water form tetrahedral species. The hybridization state of element is sp3. Aluminum chloride is acidified aqueous solution forms this one. So remember that trihalides, when you make hydrolysis here, you can see trihydrolysis. Trihydrolysis and hydrolysis in water form this one. The hybridization state of M is sp3. And next, aluminum chloride and solution forms octahedral. All good?
Yeah.
Next. As much as the reactivity is concerned, in air, they will form E2O3. With nitride, they'll form En. Okay. You notice that this nitride formation is not observed with indium and thallium. Rest all will give. Okay.
Yeah.
Next. As it comes to aluminium added to acid, it will become Al plus 3, releases H2 gas. And when it comes to NaOH, it will become NaLOH4 minus and H2 gas. So which means in both the cases, it can release H2 gas. But if you add it to the concentrated nitric acid, remember that concentrated nitric acid, so that will be making the surface of the aluminum as the passive form. So reaction will stop. So that's the
Hmm.
protective layer which it forms. By chance, if you notice TlI3, which means you should remember that thallium here is plus 1 and iodine here is minus, I3 is minus 1. Okay. Next. General reactivity towards halogens is E with X2 is becoming EX3. Okay, beta.
Yeah.
Right. And you see the anomalous behavior of boron, if you compare, correct? Unlike others forming these hydrides and water complexes, boron cannot form that easily. All right, six definitely no. Next, the lone pair can attack on BF3 here, forming this kind of uh, complex form. I mean, the salt formation. So we call this as a Lewis acid and Lewis base reactions. Okay. Next, this does explain the fact that there is no empty d orbital. BF6 3 minus is not available. I mean, it cannot be made because of the unavailability of d orbitals. Next, see, this is one thing we should remember how the borax on heating will become sodium metaborate and on further heating will become boric anhydride. This is called boric anhydride form. Okay, next. Notice the uses. Boron being the extremely hard refractive solid of high melting point and low density and very low electrical conductivity, it finds many applications. Okay. Boron fibers are used in making bulletproof vests and light composite material for aircraft. Okay. B10 has high ability to absorb neutrons and therefore used in metal borides in nuclear industry as well. Acts like protective shields. Okay. Next, aluminium. Aluminum is used, I mean, it is bright silvery white metal with high tensile strength. It has high electrical and thermal conductivity. Next, aluminum is extensively used in industry. It forms alloys with these metals. Finished? Next. Now look into the carbon family. Carbon is the 17th most abundant element by mass in the earth crust here. And you see, naturally occurring carbon contains two stable isotopes, okay, 12 and 13. In addition to that, uh, it has a third isotope which is radioactive, C14, which is still present. And the radioactive isotope has half-life of 5770 years, and that's why it is used in carbon dating. Next, silicon is the second, most abundant element on earth crust in the form of sand and different materials, and it forms silicates and silica, okay, mainly used in components of ceramic, glass and cement. Next, it group 14, we have flevorvium, which is synthetically prepared from radioactive element, that is below lead. Ultra pure germanium and silicon are used in making transistors and semiconductor devices. Got it? And you see, the flevorvium has the electronic configuration like this: 5F14, 6S10, 7S2, and 7P2. Later, you can see here the size is gradually increasing. Okay, of course, there is some closeness between the elements, but overall, it is always increasing order. Next, as the smaller size is observed, silicon to germanium to tin, and slightly increasing ionization from tin to lead is consequence of poor shielding effect intervening D and F orbitals. So you can notice this is the important orders that we need to perceive from here. So one is the ionization. So delta H of I, ionization here, if you notice, the highest is for carbon, correct? Next is for silicon, correct? And thereafter you would have germanium, lead, and then comes tin. So exception is at that last case. Similarly, electronegativity, if you compare, we have carbon, then silicon, germanium, lead, correct? But these are all least as compared to that of, sorry, this is not lead, this is tin. This is compared to that of lead. This is the order. Next, if you compare the melting point here, you can notice that melting point carbon definitely will be the highest form in the form of a graphite, correct? And then comes silicon, then germanium, then again lead, then tin, correct? While if it comes to boiling point, now see the difference here. If it comes to boiling point, carbon will still be greater than silicon, then germanium, and here you will get this as lead, sorry, tin, then lead. Got it? Which is a regular order. Mhm. Next. Carbon and silicon are non-metals, while germanium is metalloid, where tin and lead are soft metals with low melting point. Okay. Unlike group 13, here they will show +4 and +2 oxidation states. +4 is their group oxidation state. And you see the tendency to show +2 oxidation state increases in the sequence here from germanium, tin to lead here. Okay. And tin in a +2 oxidation state is an excellent reducing agent. Okay. While in the +4, They all act like a strong oxidizing agents. Okay. See, use this word electron precise. Electron precise means they have exact number of electrons to form octet. There is no lone pair on it. There are no empty orbitals on it. So carbon requires four hydrogens, and so that it can complete its octet. So it has four electrons only. That's why it is called electron precise. And next, if it comes to halogens here, as much as this, see here, halides undergoing hydrolysis have a tendency to form complexes, accepting electron pairs from donors. Example are this: silicon SiF6, GeCl6 2 minus, and SnOH6 2 minus exist, right? Where the hybridization here is sp3d2. If you compare their reactivity, they would usually have two types of formation, EO and EO2. Silicon oxide only exists at high temperature, correct? Otherwise, you will not see silicon having that O easily. Okay, so this one. And next, oxides in higher oxidation state are generally more acidic. That's why you can see dioxides here. Carbon dioxide, these three are oxides, whereas SnO2 and PbO2 are amphoteric in nature. CO is neutral, GO is distinctly acidic, whereas SNO, PbO are amphoteric in nature. Okay.
Hmm.
Now, only tin is most reactive in water, the two with heating on steam. Otherwise, none of them will react with water. Next, reactivity towards halogens. They will all react with the halogens, correct? And they can form both MX2 and MX4. One thing you need to learn is that this one exceptions are SnF4 and PbF4, correct? So these two, which are still ionic in nature, keep that in mind. While PbI4 does not exist because PbI bonds initially forms due to reaction and does not release enough energy to unpair 6s2 electrons and excite one of them to higher orbital to have four unpaired electrons around lead atom. Got it? And next, GF4 is more stable than X2, whereas PbX2 is more stable than X4. This is because of inert pair effect. Okay. Now, if it comes to hydrolysis, right? Uh, when it comes to hydrolysis of SiCl4, you can see water can attack silicon here to convert that into 1,1-OH coming out, and eventually it will convert into silicic acid. It is going to become silicic acid. Next, you can see order of catenation here. Carbon is greater than silicon, germanium, tin. Lead does not show any catenation. This is important point, that how the bond energy varies. You can see carbon has the highest single bond, then silicon, then germanium, and then lead. Okay. Carbon has three main allotropes that includes diamond, graphite, and fullerenes. In generally, the bond length of carbon is 154 picometers. Okay, and that's what is maintained in diamond. But as it comes to graphite, the length decreases because of the double bond character it has. So on this particular side, you'll see carbon bond is stronger, but between the two layers, the bond length is very high. So it's easy to break between the layers. So you can see diamond is the hardest substance on earth, correct? It is used as abrasive for sharpening tools, making dies, and manufacturing of tungsten filaments for electrical bulbs. Graphite, on the other hand, as a distance between two layers is 340, it has held by weak van der Waals forces. It is composed
Hmm.
of planar hexagonal rings of carbon atom with a bond layer of 141.5 degrees. Next, you see, graphite conducts electricity along the sheet. Got it? Therefore, it is very soft and slippery. While graphite is used in high lubricant in machine running at high temperatures, whereas you can see lubricant in the machines can graphite can be used as a dry lubricant.
Hmm.
Fullerenes. See, this is an important line that you need to know. The sooty material formed by the condensation of vapors of carbons into a small C60 type of molecular structure is what we call it as SUSI, right? Sorry. With a smaller quantity of C70 and traces of fullerene consist of even number of carbon atoms up to 350 and above. Okay. Now,
Hmm.
because they have a smooth structure without having a dangling bonds, important term. See what are dangling bonds? That means dangling bond means having open valencies. Like diamond graphite has open valencies, while graphite does not have any dangling bond. So that's why the purest form of carbon is considered as fullerenes. So I'll write down that also. So the purest form of uh, purest form of carbon is fullerenes. Okay, beta. In
Hmm.
C60, which we call it as Buckminster fullerene, correct? It consists of, let me mark this first, soccer ball known as Buckminster fullerene. It consists of 26 membered rings. Okay, correct. 6 membered ring are 20 and 12 5-membered rings. It has 6 membered rings fused with 6 membered ring as well as 5-membered ring. But 5-membered rings are only fused with 6-membered rings. Okay,
Hmm.
this is a typical structure how it looks like. This ball-shaped molecule has 60 vertices and each one occupied by them is also containing one single bond and one double bond with CC distance as 143.5 and 138.5 picometers. The spherical fullerenes are also called as buckyballs in shorts. In short, it is called buckyballs.
Yeah.
And you know that graphite is most thermodynamically stable form here. Okay. So delta H of graphite is taken as 0 and delta H of formation values for diamond and fullerenes, if we compare, these are the formation values. Next, charcoal and coke are obtained by heating wood or coal respectively at high temperature in the absence of air. Got it? Next, these are very generic uses what you need to know. Correct? This line is important. Carbon black is used in black pigmentation, in black ink, and fillers in automobile tires. Diamond is a precious stone of measured in carats, and 1 carat is 200 milligrams. Okay, beta.
Hmm.
Right. So as much as the uh, information based question is concerned, I think this is how much you need to know. Okay.